In this video, I'll be walking through Perplexed, a medium difficulty reverse engineering problem from picoCTF 2025. I've got the binary here disassembled in Ghidra. I've gone through and done all the hard work already, renaming and interpreting the Ghidra compiled C code for us. The main function of note here is the check input function, which returns a boolean. Interestingly, it returns false if the input is valid and true if the input is invalid. So that's a bit weird, but moving on to the main chunk of the check input function. So the function first checks if the user input is 27 characters long. If it is, then the function defines a secret array of bytes, which will be used later to check against the user input. We can see that there is two loops here, one that iterates on each byte in the secret array, and one that iterates through each bit of each one of those bytes. So this is a bit weird at first glance because the user input length is checked against 27 characters, and the secret array length is 23 characters, or 23 bytes. So let's keep that in mind. There's also a key insight here in this line. If input bit index equals 0, then input bit index equals 1. This skips bit 0, the most significant bit of each input byte. So each input character only contributes 7 bits instead of 8. Now the math kind of makes sense. 23 secret bytes times 8 bits equals 184 total bits needed. 184 bits divided by 7 bits per input character equals 26.3. So we're going to need 27 input characters. Secondly, we can see that there's a bit of bit masking going on here. The input and secret bytes are being left shifted by 7 minus the current bit index to create a bit mask. The bitwise AND operator is then used with the byte values. The AND31 section of this code just ensures that the shift amount stays within a valid range. This creates a bit mask to isolate specific bits and then compares if they match. If any bit doesn't match, the function returns true, which means it's an invalid input. So to solve this, we need to extract all the secret bits and repack them into 7-bit chunks to reconstruct the original flag. So I've gone ahead and written a decoder in C++, which takes the secret array as input and reverses the process to get the flag. So my algorithm walks through all 184 bits, which is 23 bytes times 8 bits, from the secret array. From each bit, it extracts it using bit masking and then places it into the reconstructed output array. The key part is tracking 3 counters: the input bit, which is the bit that we're reading from secret, output character, which is the character we're writing to, and the character bit, which is the bit position in the current character. So when character bit reaches 8, we'll reset it to 1, skipping bit 0 again, and then move to the next output character. So we are replicating the original algorithm with bit skipping behavior. Running this gives us the flag by reconstructing the original 27 character input that would pass the check. So the reason why this encoding scheme is possible is because ASCII characters are actually only 7 bits. The standard ASCII uses values 0 to 127, which fits perfectly in 7 bits. The 8th bit, which is the MSB, in each byte is traditionally unused for basic ASCII text. So the challenge author took advantage of this. They compressed the flag by packing the bits more efficiently. Because we know the MSB is always 0, we can skip storing it entirely and instead only store the significant bits. This lets them fit more data into fewer bytes, which is why 23 bytes of secret data expands to 27 input characters.